Hello everyone, welcome to lecture 4. This lecture is about elastic waves in particulate media. Let's look at the content. Content of chapter 7 here have 8 sections, and in this lecture 4 we'll cover section 1 to section 3. So in chapter 6, just to refresh our memory, we've seen the elastic wave can be used to monitor the internal process in particulate media or porous media. So when we measure the wave propagation, and wave propagation itself doesn't change the fabric or alters any the fabric of the particulate material, so it doesn't cause the permanent effect. And we've derived the wave equation, and from that there are several modes of the wave, and P wave velocity is function of the constraint modulus and the density of the material, and shear wave velocity Vs is square root of the shear modulus over density. And also we've seen how they are correlated. These elastic moduli are correlated to the bulk modulus and shear modulus and the Poisson's ratio. And also we talked about the attenuation, and attenuation happens when the material is dispersive, so that we can characterize the material attenuation characteristic using some attenuation coefficient or damping ratio and quality factor 1/Q. And soils are particulate nature. It has particulate nature, so it has inherent multi-phase nature. So in this chapter, we'll talk about the viscoelastic model to describe the wave propagation in particulate media. And there are several models that we can use. And here we'll focus on the viscoelastic model, especially the Kelvin-Voigt model and the standard linear solid model. And this model has some special feature or the characteristic, and it assumes the linearity in the force and displacement response. And the attenuation 1/Q, the quality factor, is proportional to the frequency. And velocity is constant at the low frequencies. And there are also the other models available. One is the nearly constant Q model or the constant Q model. So constant or nearly constant energy loss per cycle. And the difference is that in here you see that the attenuation is proportional, or as a function it changes with frequency. But here you can see that 1/Q, or the attenuation coefficient, doesn't change with frequency, but velocity varies with frequency. And the last one is the frictional model, and it's a non-linear model, and 1/Q, the attenuation and velocity are independent of frequency but vary with amplitude. So in this lecture, we'll focus on these viscoelastic models. Before we start the Kelvin-Voigt viscoelastic model, let's think about what is equivalent stiffness, KEQ. And when you imagine two springs with different stiffness is connected in parallel or series, what would be the equivalent stiffness? So in here, if we assume that this is fixed and there's a force, and this will deform by delta, and the force will be split into this spring and this spring, right? So F will be sum of F1 plus F2, and F1 will be K1 times delta and K2 times delta. So, and in general, this will be K equilibrium, or the equivalent stiffness times delta. So both springs will experience the same amount of deformation. So then equivalent stiffness will be just simply K1 plus K2 because it's in parallel connection. What about in series connection? So if there's a force and if this one has deformed by delta, and delta, the total deformation or total displacement will be sum of delta 1 and delta 2. But when you think about the force, because they are connected in series, the spring, the K1 spring will experience the force F, also the K2 spring will experience the same force F. So then F1 is F2 is F3. This will be the governing equation, and K1 times delta 1, K2 times delta 2 is, I'm sorry, this is the K equilibrium, equilibrium and delta, right? So then how can we solve this one? So delta, oh, sorry, this will be wrong. Actually, delta is delta 1 plus delta 2. So then F is K over delta. So this is F over K1 plus F over K2. This is F over K equilibrium. So here, if I use different color, F and F will cancel out. So the 1 over K EQ will be 1 over K1 plus 1 over K2 because it's in series connection. So keeping in mind this kind of a schematic, Kelvin-Voigt model uses one spring and one dashpot. So Kelvin-Voigt model assumes one spring and one dashpot, and it will have C here, and this will have the stiffness of the K. So then the dashpot, so spring constant K, and the dashpot will be linear damper. So linear damper means that the resistance force increases with velocity. So F will increase with velocity of object. So this will be the governing equation for the linear damper. So linear damping occurs when a potentially oscillatory variable is damped by an influence that opposes changes in it in direct proportion to the instantaneous rate of change, velocity or time derivative of the variable itself. So if you think about the damper in the door, if you pull it very hard and fast, you can feel like very stiff resistance and high resistance. But if you pull it slowly, or if you open the door very slowly, then it smoothly opens it. So this is called a linear damper. And then we can derive the equivalent stiffness for this dashpot here. Then if we assume the oscillatory displacement A times E exponential function of j omega t, then we can put this one in here. So F will be j omega c delta. So then equivalent stiffness will be F over delta K star. So that's j omega c. So here j is imaginary number. It's the same with I. Yeah? So j is I. And this is you can see that it's in the complex number with the imaginary number. So then it deformation by this viscoelastic linear damper lags behind the force with the 90-degree phase shift. So it's a complex, or it's kind of an imaginary stiffness. So it has a time lag. But when you think about the stiffness, the just spring, when you push it, it's instantaneously, there's no delay in deformation. So this is in phase, and this is called the out of phase. And this is in phase. Okay. So then we can look at the whole model here using the K and C. The dash part has the stiffness of J omega C. This one, J omega C. So this will be the stiffness. So then, because it's in parallel, we can say that it's J omega C, right? So then, when the omega, the frequency is 0, which means that we are pushing it, or we are applying the force without oscillation very slowly. So then this becomes 0, so the K equivalent becomes the same as K. But when the omega is infinite, so we're pulling it at really, really high speed, so then the stiffness goes up. So equivalent stiffness will be J omega C almost. So it goes to infinite. So you're seeing that the equivalent stiffness changes with its frequency when you have dashpot in that system. So if we solve the wave equation using this kind of system, then you have constitutive equation with extra term here with the variable C1 and C2. So this is the damping part. So before, when we assumed that non-dispersive media, this term was not there. So there was no this term. Now, because of this C term, we have these two components here, and also here in the shear part. So then, using this constitutive equation, if we put it in the force equilibrium equation with the F equals n A, right? This is the acceleration, and this will be the F, right? And this is the mass. And if you assume the particle motion in the x direction for only the p wave mode, and you end up with this wave equation. So before it was just a Vp naught square, right? And now you have this term because of the damping, because of this the linear damper. See. So then this will be the same with the shear wave. So you have this kind of a term for the shear wave, and when the omega goes to 0 and this goes to infinite, and oh no, sorry, this is the omega naught. The Vp will be the wave velocity, and omega naught will be the material property or reference frequency. And solution, we can solve this wave equation by using this oscillatory displacement with the gamma asterisk, gamma star, with considering the attenuation. And then gamma star will be derived as follows. So omega over Vp, the p wave velocity at very low frequency. So here Vp naught is the p wave velocity at low frequency. Okay. So then, what about the attenuation? So we have this gamma asterisk, and here kappa, and we have an alpha term. Alpha is the attenuation coefficient. And if we solve this one by replacing the gamma in the wave equation, you get the attenuation alpha, which is minus imaginary part of the gamma asterisk, and this will be the final equation. And we can also get the kappa by looking at the real number here of this gamma asterisk. Then you'll get this equation. So then phase velocity, I think you will remember the phase velocity is, if it's omega here, and phase velocity is this one, right? So this is the phase velocity, and the tangent was the group velocity, as you remember from chapter 6. And phase velocity is defined as omega over this wave number kappa, and you can derive this equation. So you can see that the phase velocity changes with omega, the frequency. And yeah. And also we can get the attenuation coefficient using this imaginary number, and this will be the full equation. And if we assume that omega is very low frequency, goes to 0, so then we can simplify this attenuation equation. And phase velocity too. So when the omega goes to 0, you get this equation. Oh, not this one. So this one, yeah. So when the omega goes to 0 here too. Very low frequency. So the phase velocity is approximately constant. You can see that here it doesn't contain, this equation doesn't have the omega here, but attenuation is proportional to the omega square, almost, in low frequency. So if you plot these two equations, the one I showed you here, so this one, the alpha, and the VP, the phase velocity equation, then you have this kind of a plot. So the phase velocity changes with its frequency. So in the low frequency, so this is omega naught, is actually the natural frequency, or you can say resonant frequency or characteristic frequency. Below the characteristic frequency, wave velocity doesn't change much, but when the frequency is high, the velocity goes up. What about the alpha here? Alpha times Vp naught over omega is the same with damping coefficient. So damping coefficient, it increases proportional to what, omega square, almost. This damping is proportional to omega square when the frequency is lower than the natural frequency, the resonant frequency. But as you go further up, it's not resonance, sorry, it's a relaxation frequency. Further up, it can also decrease this again. So attenuation effectively filters the high frequency component. This limitation has almost no impact on the practical problems. And one of the limitations of this Kelvin-Voigt model is here, because in reality the frequency or the upper bound is there, so it doesn't go up infinitely with the frequency. But in the Kelvin-Voigt model, it doesn't capture its spectral response. So people have thought about improving the Kelvin-Voigt model, and they attach the K1 here. and we're gonna talk about this one in the in our Zoom class. So section 7.2 is about the dispersion when the wavelength is short. The frequency content of the wave in particulate media actually have a wide spectrum. So depending on the frequency, you have different wave velocity and also the wave length. And when it's very important to look at the spatial scale between the wavelength and your heterogeneity of your material. For example, if you have a layered system like this, and when the wave comes in like this, then L, the thickness of the layer, and relative to its wave size is very important. And also, when we think about the particulate material, if the particle size is A and the wave length lambda, whether the wavelength is less than the A or larger than A, the wave velocity or the wave propagation behavior will be different. So lambda versus layer thickness or grain size will affect the dispersion behavior, and also the period versus the internal temporal scale in the soil will also affect the wave velocity and propagation. So let's look at how the spatial scale affects the dispersion, the attenuation behavior. Let's think about the monocyte lumped mass. Could be just like particle packing, the grain pack, sand pack with some internal particle size of A, like this. And these are all connected with a spring. And then force and deformation relation will follow the Hooke's law. So then we have force and deformation relation and the equation of the motion for a single particle. And if the number of spring is n and the particle number is n, then we get the n similar equations. So we can solve the a series of equations. And we can also assume the oscillatory deformation, the particle motion, as a time exponential function with I and kappa x minus omega t. Then we'll get this wave motion equation for a single particle. And if we solve, omega will be correlated or will be derived as a function of stiffness and the mass and the wave number kappa and the internal scale A. Then according to the phase velocity definition is the secant slope of omega over kappa. Then you have this equation, right? And we can also look at the kappa here. Kappa is 2 pi over lambda. So then this all becomes more as a function of the lambda. So if you look at 2 pi over lambda and 2 lambda over A pi, so pi 2 over 3 lambda sine and pi A over lambda. And V lambda, let's say that the V lambda is the velocity for long wave. Then we can simplify this equation into here, like this. And for the group velocity, by definition, is the tangent slope of the omega and kappa curve. So d omega over d kappa, and you get this equation for the group velocity. So the network acts as a low pass filter because when you solve this one, you have this kind of figure. I'll explain this figure later. And look at this equation. The kappa time a over 2 is 2 pi. When it's the 90 degree, this cosine kappa a over 2 becomes 0. So the group velocity goes to 0, which means that when the internal scale makes the whole kappa a over 2 becomes 90 degree, there's no energy transmitted. So then network acts as a low-pass filter. That transmits the wave with lambda is larger than the 2a. So when the lambda is smaller than the 2a, so then it will be scattered or it could be reflected. But when the lambda is larger than the 2a, then it can transmit, but still there's some amount will be filtered out because of this characteristic. So as the lambda approaches 2a, the maximum restoring force is excited on springs as neighboring masses are in opposite phase. So here you can think of like one is moving in this direction, and then this will compensate the other direction, so that one is moving in here and the other is moving in this direction. So then they will kind of compensate so that it becomes 0. So if you solve this equation for the phase velocity and the group velocity, and when you plot it against the lambda over a, because we can, here the kappa is 2 pi over lambda, so then the velocity changes with its wavelength as follows here. So when the wavelength is larger than 10 times of the internal scale, for example the particle size, then group velocity and phase velocity are the same, and it doesn't change with the wavelength. But when the lambda is less than 10 times of internal scale, then you can see that the group velocity decreases and also the phase velocity decreases very fast. So wave propagates through the discrete medium as if in a continuum when the wavelength is much larger than the internal scale. So when the lambda is larger than a, at least 20 times, then the wave length is like this big, and particle will be tiny. So then it will feel as a continuum media. But when the wavelength approaches the internal scale, the group velocity decay until it reaches the group velocity of 0, when the wavelength is 2 times of the a. And material with the internal spatial scale are inherently dispersive due to this kind of nature, or low-pass filter nature. So as the particle becomes bigger, or it becomes more bigger, then now the wave can feel the particle and this as a discontinuous media. So some of the wave will bounce back, like reflection, as we talked in chapter 6. So this analysis applies to all scales from atomic level to layers in natural deposit. Actually, this kind of a dispersion is called a Brouillin dispersion or Brouillin effect. In optical science, in optics, they call it also the Mie scattering. So it also applies to the electromagnetic wave and the light. So the equivalent discrete stiffness K of the medium can be expressed as a function of the constant modulus M, and the velocity dispersion in layered media, different thickness, mass, and velocity all need to be considered. So you can see that A is involved as a parameter here. In summary, when the wavelength is much larger than the particle size or the inclusion media, or for example, if we have like solid inside, you have some speckles, some inclusion, then the the size of the inclusion will be d, and if it's bigger than the pi d, then it's gonna be equivalent continuum. And scattering energy is will be proportional to d cube and omega to the 4. When lambda is similar to the inclusion diameter and the phase scattered, and when it's much smaller than that, then you get the reflection or refraction and mode conversion. In particulate material, this all comes down to a particle diameter. When the particle diameter is the wavelength is greater than the 10 times of the particle diameter, then it can be considered the equivalent continuum. And when it's less than that, you need to consider the reflection and refraction. And when it's close to 1 or close to less than 10, you will have high dispersion and low pass filtering. Okay, in section 3, we'll talk about the effect of vertical confinement or the effective stress on the particle stiffness. The soil stiffness, small strain stiffness. When you confine the soil more with the higher stress, the skeleton stiffness also increases through the stiffening of the contact. What it means is when you have soil pack in a container, and when there's small amount of stress, maybe like 1 kilopascal, then this soil will have like 1 kilopascal, just for example, of the stiffness. But if you have increased the effective stress by like 10 times, now that this is the sigma v prime, then the stiffness of this one will increase because now the soils are more confined, so that the contacts are more like close to each other and they are compressed. So that it's called a stiffening. The contacts get stiffer. So it's very important to understand the contact behavior and stress-dependent stiffness, because that's the nature of the granular media or particulate media. So there are different models to consider the different forces or the fundamentals between the particle, at the particle contact. And Hertz and Mindlin theory is to consider the contact behavior between two spheres, and DLVO theory is to consider the electrostatic force between two particles, and conical model is when you have this kind of a cone on a flat surface, so you're pushing it down, and what will happen to the contact as you push this conical contact to the rigid surface. So general form for the stress distance curve is F equals V and R theta. And here the V and the theta are constant. This is a kind of variation of the Hooke's law. And R will be stiffness. V will be the R is the displacement, and the V will be the stiffness. So you can imagine that there will be some R by the F here. So contact theory or contact model or conical model, they are looking at the contact behavior or the contact radius or the force chain between the contact. So I guess these are more detailed in previous chapter, in chapter 4, and the main idea is that when you have two particles at this amount of the contact area, and when you have two particles with much larger area, the stiffness changes even though the two grains have the same stiffness and the particle size are the same. So here contact area is AC, and here the AC prime AC prime is much larger than the AC. So then what will happen to the deformation? So here, if we have a F to get the deformation by delta for this contact area AC, but because the now AC prime is much larger, to get the same amount of delta, we need much higher force to induce the same amount of deformation delta, because now all the force will be distributed over the larger contact area. So this is the main idea of the Hertzian contact model. And when we derive the stiffness, tangent stiffness, and this becomes, this equation becomes like this, so that dF over dr becomes theta times v times f over v to the theta minus 1 over theta. So then if you manipulate this, you can see that the tangent stiffness of these two spheres is function of force. So if you applied higher force, then stiffness will also increase. So that's the main idea of the contact model. So then what will happen? Can we correlate this one to the wave velocity? So what about the p wave velocity? P wave velocity, Vp is same with square root of the constant modulus over rho. And if we apply this one here, then this becomes v times sigma zeta minus 1 over 2 zeta. And you can see that this can be replaced with xi. So now it's v prime sigma xi. Or it can be simplified to alpha times sigma beta. And here the xi and v prime is constant. So large field particle Hertzian contact model, Hertzian contact controls a small strain deformation. So in this case, theta is 3 over 2. So then the xi is 1 over 6. And when it's Coulomb force, which is electrostatic, force, then theta is minus 2, so xi is 0.75. And double layer repulsion, xi is 0.5 to 0.75, and van der Waals attraction is 0.67. So what does this power exponent means? Power exponent means that when you increase the stress by maybe like 100 times from 100 kilopascal to 200 kilopascal, then Vp increases to this beta exponent or the xi exponent. So when the xi is 0.61, you have some amount of increase in velocity, and when your xi is 0.75, the increment will be much greater. So as the power exponent or the xi gets bigger, it means that the wave velocity changes more sensitively to the change in stress. So small strain stiffness more sensitive to the state of stress in fine grained soils than in coarse grained soil. Why? Because in fine grained soil there is some electrostatic force involved, so that the xi of clay is much bigger than sand. Xi of sand. Okay, I think I don't need to go over the contact behavior of the Hertzian contact theory. So please read the chapter 4.1, and it's very intuitive, and you can also derive the equation and plot the equations to check what all the equation means. So you can see that the force, as the force increases, deformation decreases. Although the rate of deformation increases, decreases. And for the spherical contact, the Hertzian model derived the contact radius here, and you can see that the RC is, when you look at here, the RC is the contact radius, and contact radius is function of the vertical stress here. And then, if you relate the deformation with the contact radius, then you can derive the tangent elastic modulus of the particulate skeleton for uniaxial loading. So here you can see that the tangent Young's modulus is function of its given stress, and also the grain modulus, the shear modulus of the grain, and the Poisson's ratio of grain. And this kind of elastic contact or stiffness can be derived for different packing. So when you assume the mono-sized sphere, so it's a uniform sized grains, although you can say it's glass bead, then it can be packed as a simple cubic packing, or face-centered cubic packing, or hexagonal packing, and it will all generate the different porosity or different void ratio. And face-centered packing, modulus, elastic modulus will be related with the Poisson's ratio. So all can be related to Poisson's ratio of the packing. So if you think about this, when it's the simple cubic packing, when you apply the force, there's no lateral deformation. But here, when you apply the force, there will be some lateral deformation, right? So for the same amount of Poisson's ratio of the material, for example, here, like if you think about the quartz grain will have the Poisson's ratio of 0.2 to 0.3. Then body-centered cubic packing or the hexagonal packing has the largest Poisson's ratio, and random packing has the lowest Poisson's ratio. But still, the Poisson's ratio of the packing is much smaller than the Poisson's ratio of the particle itself. So here the Poisson's ratio 0.3, but still it's less than 0.1. So the elastic Poisson's ratio for the dry sphere pack has very low value. And then if you know the skeletal Poisson's ratio, then this can be related to the shear modulus, because from the Hertzian contact model we can get the E tangent, right? E tangent and nu sk, the skeletal Poisson's ratio, then we can get the shear modulus of the skeleton. So, and these are the shear modulus for different packing, and simple cubic packing, and body-centered cubic packing, and face-centered cubic packing, and the tetrahedral packing. And here Cn means the coordination number. Coordination number means that how many particles are in contact per particle. So, for example, simple cubic packing. Let me go back to the this picture. One particle will be in contact with 4 particles in the same plane. Also at the top there will be one more, right? And at the bottom there will be one more. So there's this one and there's this one. So in total the coordination number will be 6. But here you have a more coordination number, and also here it's gonna be in between 6 and the FCC coordination number. So FCC coordination number is 12, and hexagonal one is about like 8. So then, as I said, for the random packing, you can derive this shear modulus using Hertzian contact model. And here coordination number is given in that equation as a function of coordination number, and void ratio is also inside. And the most important thing is the shear modulus is proportional to the isotropic confining stress sigma naught to the 1/3 of it. So to the power of the 1/3. If the Cn is correlated to the void ratio using this equation, 13.28 minus 8 E, then you can get, you can simplify this equation. GSK is so with the power exponent nu here. So it is similar to what the Vs equation. We're gonna talk about this one later. And we can explore the different packing. Right? There are no closed form solution for the shear modulus of the random packing subject to anisotropy loading, but for the stress anisotropy, when it's not anymore the anisotropic confining stress, so sigma h is not the same with the sigma v, then now that you have a sigma m and the sigma p, that's the principal stress, then we have a GSK and the shear modulus of the skeleton in different form. And loss, say attenuation. Loss mechanism in dry particulate material varies with strain level. At very small strain, the relative displacement between the centers of the particles can be very small and may not cause interparticle friction. So it means that when it's dry, the damping is really low, but as it becomes saturated, that you have a more frictional loss because of the fluid motion. Therefore, the energy losses in perfectly dry media at small strain take place within the material of the particle. So it's kind of internal friction. So it means that you get the wave or the vibration attenuate within the particle itself because of the material damping of this quartz grain, or it could be a kaolinite grain. As the strain increases, atomic bonds begin to break at the contact as well as within the material, and it absorbs the monolayers. The presence of these monolayers can increase attenuation by an order of magnitude, and frictional losses at the contact develop. So it is also together. So rate of independent losses, it's Mindlin contact model, it's called. And for an anisotropically loaded simple cubic packing, there are some frictions at the contact, and it develops the shear stress and frictions and causes the energy dissipation. Let's read this paragraph. The mobilized shear stress tends to increase to infinity at the contact edges. For a limiting interparticle friction coefficient mu, the maximum shear stress can be mobilized tau f is mu times sigma. Hence the slippage occurs at the contact edges where tau is larger than the tau f. In turn, the distribution of the contact shear stress in the non-slip region must change to preserve the equilibrium in the horizontal region. So the annulus of the slippage along the periphery of the contact causes irreversible energy losses. So basically it says because of this geometry, you get the high shear stress at the edges, but in reality, these all needs to be equilibrated, so that there's a reaction force and a resistance. So then you get there's some movement when the shear stress is bigger than the frictional resistance, and this slippage will occur the energy losses along the peripheral, so along his edges. So it's this kind of a physics is behind this Mindlin contact model, and because of that 1 over Q, or the damping coefficient, can be derived as a function of shear strain tau, not the gamma. And gamma, here the gamma T is the threshold strain between particles that causes global slippage at the contact, and mu is the friction coefficient. And gamma TV can be threshold shear strain can be derived as a function of Poisson's ratio and the shear stress, the normal stress, and the mu, the friction coefficient, and shear stiffness of the grain too. So frequency does not affect the frictional loss. So here in Mindlin contact theory, this is applied to the dry particulate material or the granular material. When there's no water, and it's all about the shear strain relative to the threshold shear strain, and this kind of a slippage does not relevant to the frequency. So frequency doesn't affect the this kind of a loss, the energy loss in Mindlin context. Okay, that's all for the lecture 4. Thank you for listening.